Welcome to Biomaterials. Today we're going to talk about stress and strain. And when we're thinking about biomaterials, one of the key parts of biomaterials, one of the key considerations of biomaterials, is stress and strain. Basically, strain is related to how much deformation a material encounters when it is under stress, which is related to how much force we're putting on it. So because almost all materials need to experience stress to some extent, being able to describe stress and strain mathematically is critically important to the function of biomaterials and ultimately the function of bioengineered devices and treatments that use biomaterials. So we're going to talk about stress and strain. So the first thing we're going to do is elaborate a little bit more on why we might care about stress and strain in the context of bioengineering and biomaterials. Then we're basically going to proceed with sort of a bunch of definitions related to stress and strain. There's not just one flavor of stress and there's not just one flavor of strain. So when we're thinking about stress and strain, first we'll talk about normal stress. And then we'll talk about strain, and in particular, we'll talk about engineering strain. There are basically a whole bunch of different ways to characterize exactly what we mean by stress and exactly what we mean by strain. So I'll start. So first, I'm going to list out these the topics, and we'll sort of cover each one in more detail. Then we're going to move on to what's called true strain and true stress. Finally, we'll move on to shear stress and shear strain. And how they relate to bioengineering. So this is the outline for what we're going to talk about today. Let's first start off with why we might care about stress and strain in general. So when we think about stress is basically related to it's primarily driven by the forces that are on a material. So for example, if I have this banana and I want to pull it apart, I'm applying force to the banana, but then when we sort of zoom way down to the scale of the banana, each little bit of the Velcro in the banana is experiencing some stress, and ultimately it's the stress that causes materials to break. So when we think about stress is the primary factor in what governs whether a material will break. So it's related to stress is related to force. We'll hash out the precise definitions later. But the key takeaway from stress is it allows us to answer the question: will a material break under use? And that you can imagine for primarily structural things. For example, if you're designing a hip implant, or everything from hip implants to hypodermic needles need to have some kind of stress analysis to make sure that when we're using them in their desired way, that they don't break. The second thing that we want to analyze when we're thinking about stress and strain is strain, which is essentially related to deformation. So for example, if we have some biomaterial, maybe it's Play-Doh, maybe not, but if we have some material and we apply stress to it, that material deforms. And so materials deform when they're experiencing this stress, and that deformation in quantitative ways we can quantify as strain. And of course we have a few different definitions of exactly how we quantify it later, but strain is related to deformation. And you can imagine in some contexts, this strain and deformation can be just as important as a material as a material breaking in certain contexts, right? So as a design engineer, well, okay, maybe this material didn't break, but did it deform too much? So will a material deform too much? Or maybe in some contexts we want that deformation, or not enough, underuse. So, so this has important considerations. For example, if you're designing the springs as part of shock absorbers in a prosthetic, for example, like a prosthetic ankle or something like that, maybe we want some amount of strain because to sort of simulate the experience, the natural deformation that would occur during ordinary limbs. We want to recapitulate that. Or you might have seen some high performance prosthetics for amputees where an entire foot can basically be replaced with sort of a springy structure that connects to the limb stump. So instead of having a foot like this, it's an amputee is basically replaced with this sort of spring-like structure. And sometimes we want deformation in our thing. Another example for where we might want deformation is if we have a stent, and then we want to expand that stent. We want to use like a balloon catheter to basically expand a stent to prop open an occluded artery. So in this case, we want strain, right? So, but the most important thing in all of these cases is being able to use the crystal ball of engineering to predict when these things are going to happen. So stress basically says, hey, will this material break? Will my prosthetic banana break apart when I apply too much force, or will it have sufficient strength to do together? Well, in order to do that, we basically need to predict how much stress the material is under, potentially at all points in the device. And then when we think about strain, will a material deform or too much under use? And not part of this lecture, but part of future lectures, we'll be discussing the connection between stress and strain, where basically, usually for most materials, the more stress it experiences, the more strain it undergoes. So, and oftentimes they're proportional to one another in certain regimes. So that's why we care, right? We want to make sure our stuff doesn't get too bendy. We also want to make sure our stuff doesn't break. And by knowing the material properties and the geometry and the forces that we apply to these things, we can make all of these connections. So that's why we care about stress and strain. We can now let's sort of move on with our sort of our formalized definitions of stress. And in particular, we'll start with normal stress. So when I think about normal stress, I'm not just talking about stress that's normal, like common, that we experience in our everyday lives. When we're thinking about normal stress, we're in the context of engineering, we're thinking about stress that is associated with forces that are perpendicular to a surface. So normal stress arises from forces perpendicular to a surface. So if you dust off your high school physics notes, you might have said, oh yeah, I remember, like, the normal force, from a surface. Well, there's stress that arises from forces who have components that are normal to a surface. So so to sort of think about what happens to objects when we apply forces to them, just imagine a little thought experiment here. Imagine I have some cube, let's say like this, So here's my cube, and now let's say I applied some force. Let's say I applied some force F to this cube. Take a moment now, pause and ponder, what would happen? To the cube. Well, if I applied just one force this way, this cube would actually sort of start accelerating up to, out of the page, out of the field of view, right? If I applied some force, force equals mass times acceleration. So when we're talking about normal stress, we almost always talk about it in the context of balanced forces. So when we're thinking about stress and materials balance, we're usually talking about it. So usually we're talking about balanced forces, or the stresses that arise from balanced forces. So I'm tugging on my block 1 point, tugging on my block down here. The block doesn't have unbalanced forces, so it's not really accelerating. So when we're sort of analyzing materials and material properties, we're oftentimes considering sort of this case where forces are equal and opposite, and now I'm sort of zooming in and imagining what happens to the material right here. So the answer to this question is the cube would accelerate if we had only one force. So usually we're considering equal and opposite forces like this. I guess stress technically would arise if I had an unbalanced force, but that's tricky to model. So, and sort of outside the scope of what we're going to cover here. So in this case of equally balanced forces, you can kind of imagine a slice of this material right here. So if I imagined a slice of this material right here, when I look inside the material, so forces are something that we sort of apply on the scale of a whole object. But if I imagine this, if I sort of zoom into this slice of this material right here, this forces are distributed within objects. So forces are distributed inside of objects over their cross-sectional areas. Right? So forces are distributed. So forces just are distributed over cross-sectional areas. Not always uniformly, but often uniformly. So often uniformly. So what do I imagine? Well, this force actually gets broken up, and sort of, each little bit of this cross-sectional area supports some of this overall force. So if you can imagine, I could sort of imagine breaking up this cross-sectional area, into a whole bunch of little chunks, and each of those little chunks support some of that overall force. And on the top face of this cross-sectional slice, it pulls up, and on the bottom face, it of course, would pull down, if we could sort of see underneath this block right here. And we call this sort of division of force over the cross-sectional area stress. So stress basically has units of force over area, and you can imagine it's sort of divided up. It's divided up in this way. So in SI units, which is what we'll try to use mostly throughout this course, force would of course have units of newtons. Area would of course have units of meters squared. So stress would of course have units of newtons per meter squared, and oftentimes this newton per meter squared is given a special name of a Pascal. So that's what that. And a Pascal is actually pretty, in the grand scheme of things, pretty small in terms of like 1 Pascal isn't very much stress. So oftentimes you might see kilopascals or megapascals or even gigapascals when trying to quantify stresses in your engineering practice. So this is sort of the general idea of stress as a force over per area. Now let's talk about normal stress specifically. So normal stress, we'll give it, oftentimes stress is given the Greek letter sigma, and oftentimes we give it some subscripts, sometimes just a letter, sometimes something else. So oftentimes we'll give it some subscripts, so maybe I'll call it sigma normal. And the normal stress essentially arises from a normal force divided by a cross-sectional area. So this is basically what a normal stress is. And if you imagine a chunk of material, I take this chunk of material, it exists, it exists as its way. Then I start, then I apply some stress to it. We actually need to be a little bit careful about what area we're talking about, right? So if I have the banana, I take the banana, I'm applying some stress to it. I'm talking about the cross-sectional area if I were to sort of slice that banana perpendicular to the force that I'm applying, right? So there's a normal force like this. The cross-sectional area that I'm considering is the area of this sort of white face right here. So that's what I'm talking about. And we call it engineering. We call it engineering stress. If your cross-sectional area is equal to whatever the cross-sectional area was before the force was applied. Why do we need to be careful with this distinction? Well, if we go back to this Play-Doh thing right here, before I apply the force, this has a pretty big cross-sectional area, but after I apply this force, it stretches down to a much smaller cross-sectional area. So it can be confusing in different contexts, like, hey, which area am I talking about when I'm talking about normal stress? Am I talking about the original area? Am I talking about this smaller area? So to make that distinction unambiguous, engineers oftentimes just talk about engineering stress, and the cross-sectional area is what we consider is the cross-sectional area of whatever this blob of Play-Doh was. It's the cross-sectional of whatever the blob of Play-Doh was before I applied this force. Why before I applied this force? Well, that's what's easy to measure. I measure the cross-sectional area, and then I put this thing in its application where it's applied to forces later on. So that's what we're talking about here. And of course, the area changes are typically minimal if as long as the material doesn't deform too much under its given applications. But I digress. Normal stress, a normal force divided by a cross-sectional area, and it's engineering stress if that the cross-sectional area that you're using for this stress computation is whatever the cross-sectional area was before you applied your forces. All right, so thus concludes our discussion of normal stress. Hopefully that wasn't too stressful. Let's now talk about engineering strain. So engineering strain, and in particular, we're talking about engineering normal strain right now. So when we think about engineering strain, and sort of as I set up this idea in the very beginning of the class, when we apply forces to things, stresses arise, right? As stress is force over area. And when we apply these stresses, undeniably we'll experience some strain in the material. So engineering strain occurs when materials are stressed. So occurs when materials are stressed, and it sort of describes the amount of deformation that a material experiences. So let's sort of imagine it, right? Imagine I have my material. Some chunk could be Play-Doh, could be something else. Right, so I have some chunk of material, and it might originally have some length, let's call it L1. Then I apply force, and in particular now I'm talking about applying normal forces, some normal force. And what happens when I'm applying some normal force? Well, compared to its original length, the material gets a bit longer. So I have some original length, I apply some force, of course balanced forces. So I'm applying some force and now it gets longer. So it might have some length, let's say L2, after the deformation. And L2, if you apply forces, in this sort of tensile direction, in the stretching direction, it gets longer, right? So it deforms in the direction that you're applying forces. And we might say its deformation what we might call deformation, we'd say like delta L, and we'd say its change in length would be its final length minus its initial length, so like L2 minus L1. And but you can imagine this deformation doesn't really describe the whole picture, right? So you can imagine if I had some tiny little chunk of material, let's say I had some tiny little chunk of material like this, and I stretched it with a delta L of 1 centimeter, I'm essentially doubling its length. But if I have a much longer piece of material and I stretch it 1 centimeter, its change is sort of relatively less important, right? So deformation is sort of like an absolute, an absolute change in length, right? Where delta L would sort of have units of meters. But oftentimes, from the perspective of the material, right? If we sort of zoom into the scale of the material, the material doesn't care how many meters longer it was, it is now than it was before. Material sort of experiences a sort of relative change in length, or sort of a proportional change in length. So the material cares only about proportional changes in length. Right? It's a lot easier to get something that's 10 centimeters long to stretch it 1 centimeter than if it were only 1 centimeter long at the beginning to stretch it 1 centimeter, right? That essentially doubles its length, whereas the other one only increases it by 10%. So if we're thinking about this sort of proportional changes in length, that's where this idea of strain comes in. And so in general, strain is defined as a change in length divided by some reference length. Right, where basically if you normalize the change in length sort of as a fraction of some reference length for the material, then it sort of keeps things in proportion. And so take a moment now, pause and ponder. What are the units of strain? If you were in SI, you know, if you're working in SI, let's say. Well, hopefully you've had a chance to work it out. If you pause and ponder, the units of strain, there are actually none. It's a trick question, right? Delta L would have units of meters. If we divide its change in length by some sort of characteristic length of the material, that also has meters, so strain is unitless. Sometimes you might see it reported as a percent. Sometimes reported as a percent. All right. Now, the question is, what do we use as an appropriate reference length, right? What is the most sensible reference length that we, that we could use, right? So we want to normalize our change in length to some reference length. What is the appropriate reference length that we can sort of normalize this change in length by? Well, as engineers defined it, we sort of fall back on a similar definition. So if we're talking about engineering strain, one reference length that you can use to sort of normalize this strain is the original length of the material, right? So in a way where when we talked about normal stress, we talked about engineering stress, even though once it's stretched out, the area changes a little bit, in an engineering context, it's oftentimes easiest to sort of normalize these things by what the original cross-sectional area was. So for engineering stress, we use the cross-sectional area before force was applied. For engineering strain, this reference length that we use would be the original undeformed length of the material. So I'll call this E. Our engineering normal strain is the change in length divided by what the original length was in the undeformed state. So L1. So this sort of says, hey, if you started off with a long rope and, had a long change in length, that would be equivalent to if you started off with a short rope and had a short change in length. What the rope itself is feeling would be basically the same in those two cases, right? So, if I had a rope that was originally, let's say 1 meter, and then I had another rope that was much longer and I made it 10 meters, if I took this rope and stretched it out to be 1.1 meters, and took this rope, stretched it out, and made it 11 meters, the strain in each of these ropes in these states would basically be the same, right? It's essentially, increasing the length by 10%. So in that case, oops, sorry, I got cut off a little bit there. Yeah, so if I took a 1 meter rope and stretched it to 1.1 meters versus taking a 10 meter rope and stretching it to 11 meters, in both cases, both ropes have the same, strain, or the same engineering normal strain, in this case, in their deformed states. So, thus concludes our discussion. Thus concludes our discussion of engineering strain. Now let's move on to talking about true strain. Now, one thing you might say is, well, what was untrue? Was there anything untrue about this? What was untrue about engineering strain, right? That, there's a change in length, I divide it by the original length. There's strain right there. And, there's nothing untrue. There's nothing untrue about engineering strain, but it doesn't always necessarily paint the most true picture of what the sort of material itself is experiencing. So engineering strain doesn't always really reflect what the material. I'm going to sort of anthropomorphize the material a little bit, but it doesn't always reflect what the material itself experiences at large strain values. So engineering strain doesn't reflect what a material really experiences particularly at large strains. And what do I mean by that? Well, what I mean by that is if you imagine a little chunk, let's say this chunk of Play-Doh right here, and I take this little chunk of Play-Doh and stretch it just a little bit. Initially that first little bit of change of length, the original length is a pretty good, that describes a pretty good fraction of what it was, right? So at the beginning, the original undeformed length does serve as sort of a good baseline. So at the beginning, so at small strains, L1 is, serves as a good reference length, right? In our as a denominator in that definition of stress. But at large strains, right? So imagine I started with this material here, and I stretched it out and stretched it out and stretched it out and stretched it out. Oh, sorry, I didn't break it. I stretched it out and stretched it out and stretched it out and stretched it out. So let's say I took this material and stretched it out a lot, and then after having stretched it out a lot, I wanted to stretch it out just a little bit more. When I went to stretch it out a little bit more, that last little bit of stretching that I did, that original length is almost totally irrelevant for that last little bit of stretching. So at large strains, the initial length is kind of irrelevant. So the initial length sort of loses its relevance, and we would want to imagine we would want to use a more recent length as a comparison, right? A more, for this last little bit of stretching that I'm doing, that length just before that last bit of stretching is the more relevant length, rather than what it originally was way back when. So when we have large strains in a material, the initial length is irrelevant, and the sort of most recent length is more relevant. So, and this leads us to the idea of defining something called true strain. And when we think about true strain, we could basically say, hey, I am going to take this material, and if I were to start with its length here and stretch it all the way out here, in engineering strain, I would use this initial length to sort of normalize that final change in length by. But for true strain, what we do is we constantly update. So we constantly change or constantly update So we constantly update our reference length to the current length. So we currently update our reference length to the current length, and we break up the strain and the change in length into an infinite number of infinitesimally small steps. So break up the straining process into infinitesimally small steps. So what does that mean? Instead of describing a single strain for the overall process, we'll define an infinitesimally small strain, and I'll call this, like, let's say d epsilon true. And I'll define this increment in the true strain that something experiences, right? This sort of infinitesimally small step in strain as an infinitesimally small step in the change in length. So let's call it dl would be an infinitesimally small step in the change in overall length of the material, divided by L, which is whatever the current length of that material is. So in a sense, I'm normalizing each increment in the change in length by its current length. So in a sense, it looks similar. It looks similar in some ways to strain, only instead of having the entire delta L as one whole chunk, I'm breaking up this delta L into a whole bunch of infinitesimally small steps. And instead of using just the original length, I'm renormalizing each of those incremental steps by whatever its length currently is. So you can imagine, instead of going from 1 meter to 1.1 meters, it's almost like I'm doing this from 1 to 1.000001, 1.00002, 1.00003, and I'm normalizing each of those deltas by whatever the length was when it underwent that delta. So that's what we get here, and that's what we have here. Now, if you're looking at this, you're like, wait a second, this looks sort of, this is kind of looking a little like, I want true strain, right? You've defined an increment for true strain. I want an equation for what the actual true strain is. So if we have infinitesimally small things, and we want to add up an infinite number of infinitesimally small things, well, the way you add up infinitesimally small things in a calculusy sort of way is via integration. So we integrate to get true stress. To get true strain. To get true strain. So just to recap what's here. This is an increment in change in length. So in a sense, if I started with a rope that was like this, and eventually I ended up with a rope that was like that, I would break up the change in length into an infinite number of infinitesimally small pieces, and I would call each of those dl. And this overall straining process, I would sort of accumulate all of those dl's, normalizing each one by whatever its length was at the current step in the stretching process until it got to the final value. So we want to integrate all of these increments to get the true strain, and in a calculus way, integration is essentially adding up. So if I want to get my true strain, well, what do? I integrate all of the increments of true strain. And if I increment all of the increments of true strain, then I'm essentially integrating both sides of this equation here. dl divided by L. And the limits of integration that I would use would be whatever my L initial was before I started to whatever my L final was. Whatever my L final was over here. Or we could sort of recap it as, to sort of put things in the similar context as to when we were talking about strain. We used L1 and L2 for our initial and final states. So I could say I'm integrating from L1 to L2 dl over L. So take a moment now, pause and ponder. What do we get when we evaluate this integral and apply the limits of integration? Feel free to hop on over to Wolfram Alpha if you want to do the integration for you. All right, well, hopefully you've had a chance to do out the integral. Remember, if you integrate, we're essentially integrating 1 over x dx, only instead of x, we have L. So this ends up being natural log of L, evaluated from L1 to L2. If you sub in the limits of integration, we get natural log of L2 minus natural log of L1. And if you apply your little log rules, remember if you subtract two logs, that's equivalent to dividing what's inside of them. So the true strain from 1 going to 2 is equal to the natural log of L2 over L1. And if you wanted to sort of further, to further break things out, we could try to develop a relationship between true strain and engineering strain. So let's do that now. So if this is true strain right here, can you develop an equation for engineering true strain in terms of engineering strain? So take a moment now, pause and ponder, try to work that out for yourself using this equation for true strain and these definitions of engineering strain. Well, hopefully you've had a chance to pause and ponder and do that. I guess I wanted to describe this as a pause and ponder question. So pause and ponder. So the true strain is equal to natural log of L2 over L1, but our goal is to put this not in terms of lengths, but in terms of true strain. So if you did this, you could say this is the natural log. L2 is just delta L plus L1. So we could say L2 is delta L plus L1 divided by L1. And you could say, hey, this sum in the numerator would be the same as just each of them divided by the denominator. So that's like delta L over L1. And then L1 over L1 would just be 1. And if you look at what you have here, this is the natural log of the engineering strain plus 1. So what does that mean? Well, if you wanted to sort of plot what one looks like compared to the other, let's put engineering strain on the x-axis and true strain on the y-axis. Take a moment now, pause and ponder what the sketch of this relationship, what the sketch of that relationship looks like. All right, hopefully you've had a chance to pause and ponder. Well, when engineering strain is 0, natural log of 1 is 0, so true strain is 0. So when engineering strain is 0, true strain is 0. That's good. When engineering strain goes up, if you remember natural log, a straight line goes like this, but natural log kind of creeps up, but at sort of a rate less than what, this is essentially y equals x, right? So and a natural log kind of curves down a little bit. It doesn't asymptote to anything. It grows without bound, so it keeps growing. Grows without bound, but less than the curve like y equals x right here. Right. So what does this mean? This means when engineering strain is positive, true strain, so when engineering strain is greater than 0, true strain is less, the magnitude of true strain is less than the magnitude of engineering strain. So what sense does this make? Well, that gets back to this idea of the Plato, where when I was stretching things out at large values of strain, once I've already stretched this material out a whole lot, that last little bit of stretch doesn't really mean as much as the first little bit of stretch in terms of how the material sort of feels or experiences strain. So that basically means like the true strain that the material actually sort of feels while it's being stretched out is a little bit less than what the engineering, than sort of what the engineering strain sort of predicts how it would feel. So true strain is less than that. Now, if you notice here, I've only drawn things where we have positive engineering strain and positive engineering stress. Take a moment now, pause and ponder. Can engineering strain and or true strain be negative? So is it possible for strains either engineering or true or both? Is it possible for those to be negative? And the answer is yes. And under what situations would strain be negative? Well, this would be true if L2 is less than L1. If we go back to this definition right here, right, if L2 is smaller than L1, then we have negative deformation. So what does that mean? Well, if I take some material and instead of trying to stretch it out, if I instead compress it to a length smaller than its original amount, then in that case the change in length is a contraction rather than a stretch, and that means that it's in compression, and strain can be negative, right? So yeah, so if L2 is L1, that means it's in compression, and strain either engineering or true or both can be less than 0 because delta L is less than 0. And what does that look like? Well, if I sort of continue this line y equals x into the minus regime, this relationship between engineering stress and true stress essentially approaches a vertical asymptote towards -1. And what's up with this vertical asymptote at -1? Well, basically it's saying, hey, this material experiences an infinite amount of true strain if I were to try to squish it to be zero original length, right? If my engineering strain approaches -1, right, so if engineering strain approaches -1, then that means I've taken this block and compressed it to essentially have 0 length. And of course that's not really physically possible, so we get weird things like predictions of negative infinity for true strain in that way. But anyway, I digress. True strain true strain is related to engineering strain by this relationship here. And basically what this does is saying, hey, when you're stretching something out, you know, the material doesn't really feel like it's getting stretched. Once it's already stretched a lot, it doesn't really feel like it's getting stretched much more. And once it's being compressed, if you're compressing it, it actually starts to feel more and more and more of an intense strain phenomenon as you're kind of squishing it down and down and down into smaller and smaller and smaller of a pancake. So, thus concludes our discussion of true strain. Now let's talk about true stress for a little bit. So if you remember, when we were back at the beginning, we said, hey, engineering stress says use the original, you know, even though when I take something and stretch it out, you know, even when I take something and stretch it out, its cross section contracts. You know, use the original cross sectional area just as sort of a rough baseline for engineering stress. When I talk about true stress basically says, hey, use whatever its current cross sectional area is as a measure. As the area that stress is sort of divided over. So use current cross-sectional area as denominator to divide stress. So what does it mean? I might say, hey, I have, again, we use Greek letter sigma to sort of signify stresses. True stress would basically be whatever my force, you know, whatever I was using as my force, divided by the current AC in deformed or current state. So that's basically what's used for what's used for true stress. All right, take a moment now and prepare yourselves for a pause and ponder question. The magnitude of true stress is always bigger than the magnitude of engineering stress. So, you know, I have my Play-Doh, right? I'm applying forces to my Play-Doh. Is it true or false? True stress should be bigger than engineering stress. All right, so hopefully you've had a chance to pause and ponder. It's not always true. It is sometimes true. So what does that mean? Well, usually, it's usually true for tension, right? So if I take something, so usually true for tension, with stretching something, so with, usually true for tension, with stretch, the cross-sectional area goes down, and if stress is equal to force divided by cross-sectional area, if this goes down, this goes up. So for tension, with stretch, cross-sectional area goes down, so that means stress goes up, but in compression, well, what happens in compression? Well, when if I have some material and I squish it, its cross-sectional area actually increases, right? Because I'm taking that material and I'm now spreading it out, and now there's more area for that force that I'm applying to be distributed over. So, but in compression, cross-sectional area usually goes up, and that means that the true stress. So the true stress would go down. There are a handful of weird materials that get wider as you stretch them, but again, those are some weird properties that we'll get into in a later lecture. But for most materials, when you stretch them out, they get narrower, so that means the true stress is actually higher. And in compression, when you take most materials, when you squish them, their cross-sectional area increases, so that means that the true stress gets lower. All right. Now, take a moment now and let's try to develop a way to predict what this true stress is, right? Wouldn't it be nice if we had some way to predict what the cross-sectional area is going to be? And if we could predict what the cross-sectional area is going to be, then we could predict what the true stress is going to be. So we want to develop a way to predict. We want a way to be able to predict true stresses. And in order to have a way to predict what these true stresses are, we need a way to predict how cross-sectional area will change. Now, it turns out we have a pretty good way to do that for a handful of materials, and actually for many biomaterials, this is a pretty accurate approximation. So an approximation is that the volume of material, so I'll call this volume. I like to cross my volume related V's in this weird way to distinguish them from like V's that are used for velocities or voltages, or we use V a lot in engineering. So my volume related V's, I do a weird cross in this way. So we want to predict it. So if we say, hey, if we assume that the volume is constant, then this might allow us to basically predict how the cross section will change. So what does that mean? Well, if I think of volume, I could say, hey, my volume is equal to the cross sectional area, right? The cross sectional area times whatever its current length is. So volume is equal to cross sectional area times length. So what does that mean? Well, if I had some chunk of material and I then took it and stretched it out a bit under the application of some force, if I said, hey, the volume of this material is constant, and I knew what L1 and L2, if I knew what L1 and L2 were, and I knew what my original cross-sectional area was, I'll call it AC1 is, then that would give me all of the information I would need to essentially predict, this is the cross-sectional area. I knew what this first cross-sectional area was, then if I knew the volume were constant, this would give me all of the information I needed to predict what the second cross-sectional area is in this deformed state by assuming its volume is constant. It turns out and this is a good assumption for elastomers. And it's not too bad for soft tissue. It's a good approximation for elastomers or soft tissue. So how do we go about doing this calculation? Well, I can say, hey, my true stress is equal to force divided by cross-sectional area in this deformed state. But if I look at this relationship here, then I can say, hey, AC1 times L1 is equal to AC2 times L2. So I can basically put AC2 in terms of AC1 and L1 and L2. So what does that look like? I can say that this is equal to force. If I bring L2 over to this side, then I can say, hey, that's AC1 times L2 over, L1 over L2. Gotta get my division right. L1 over L2, which I could say is equal to force divided by AC1 times L2 over L1. Now, take a moment now, pause and ponder. What's this? And then also take a moment and pause and ponder. What's this? What's that quantity right there? So what are these two quantities? Well, this first quantity, if you go back, is actually just the normal stress, right? It's the force divided by whatever the cross-sectional area was before that force was applied. That's this right here. So true stress is basically equal to engineering stress, right? This first term is the engineering stress, but times L2 over L1. But if you look at L2 over L1, you could basically say it's delta L plus L1 over L1. And that's basically just 1 plus the engineering strain. So 1 plus the engineering strain. So you can basically include this little correction factor in your computations of engineering stress if you wanted to get a prediction of what the true stress is that the material actually experiences when its cross-sectional area changes in response to deformation. All right, so take a moment now, pause and ponder. Which is bigger? Bigger in terms of magnitude. The true stress or engineering stress. And I'm just talking about magnitudes right here. So, you know, if we're taking something and stretching it out like there, which of these is bigger? Which is bigger, true stress or engineering stress? Well, actually, it depends. And what does it depend on? It depends on whether you're in tension versus compression. So when you're in tension, 1 plus, if we're talking about engineering strain right here, so in tension, engineering strain is positive. This little factor here is basically 1 plus something positive. So sigma true is greater than sigma engineering in terms of their magnitudes. But in compression, remember delta L. Delta L is negative. So this factor here, this 1 plus engineering strain, basically is 1 plus something negative. It's negative. It's smaller than 1, but negative. So that basically means, so the magnitude of true strain, of true stress is actually less than the magnitude of engineering stress. And why is that the case? And that's and the reason is basically because AC is bigger in the deformed state, right? So so when you're squishing something, you now have more area to distribute that stress over. So the true stress experienced by each little unit of that Play-Doh is now less than it is less because there's sort of more area to distribute that force over. So in tension, true stress is usually is bigger than engineering stress. In compression, the opposite is true. All right, sorry for the pause. Now, we have just two more topics to cover: shear stress and shear strain. So, when we talked about normal strain, normal stress, we basically said, hey, I have some chunk of material and I'm applying forces perpendicular to the surface, right? These forces are perpendicular to the surface there. But that's not the only way that I could apply forces. I could apply, I have some chunk of material. I don't necessarily have to just stretch it, sort of in this direction. I can also stretch it to the side. I can apply forces that sort of do this sort of thing. So this leads us to talk about shear stress. And if I think about shear stress, it's basically when the force is parallel to the surface. So what does that look like? If I have some chunk of material, I basically apply a force that looks like this, but I'm going to need an equal and opposite force, to apply to this end. But if I apply forces just like this and this, that's going to cause this material to rotate. So actually you sort of also need paired with it some other stresses on other surfaces that kind of work out like this to sort of like keep, you have equal and opposite forces to kind of stretch it like this, but you also need sort of additional forces to keep it from rotating. So you almost get this sort of like pinch. It's almost sort of like a pinching motion, right? So if I have some chunk of material and I want to apply shear stress to it, I basically need to stretch it like this, and you can imagine sort of pinching it out. I'm taking this surface, moving it this way, taking this surface, moving it this way, but also applying some additional forces to keep that whole thing from just rotating. If I were to apply forces, like this, sorry, that's just going to keep it rotating. So I sort of need combinations of lots of forces in order to apply shear stress. And the way we think about defining shear stress, I'm gonna sort of neglect these forces, these forces right now and just sort of focus on these ones. But we still imagine this force as being distributed over a cross-sectional area. I'm just gonna draw it down here. We still imagine these forces as being distributed over a cross-sectional area. Right, so I have this force here. I'm still imagining it being distributed over a cross-sectional area like this. This cross-sectional area, and the way I look at it is imagining a little slice coming out. And I'm kind of imagining, instead of just one single arrow here, each little bit of this surface gets a tiny little arrow chilling on it, scooting it to one side, and the bottom of it gets a whole bunch of little arrows, scooting it over to the opposite side too, such that, when you shrink it infinitesimally small, this effect kind of goes away and you just sort of have this top and bottom shear stress going on. So this is basically what shear stress is, and it's basically it's defined in the same way. Instead of using a Greek letter Sigma for shear stress, people typically use tau. It still has a definition of force over area. So we'll just do force parallel to the surface. Of course, you need to watch out because you can also have forces parallel in another, right? There can be any number of directions that you can have a force parallel to a surface, whereas perpendicular is always just perpendicular. But if you sort of take all of that, you know, the resultant parallel force to the surface and divide it by this cross-sectional area, that's what we're talking about, right? So if I sort of look at the banana right here, when I'm applying shear stress to the banana, I'm now kind of causing this to slide over. I'm considering this cross-sectional area of the white face right there. So this is what we call shear stress. All right, and you know, so why do we even care about shear stress? Well, materials often fail when shear stress is greater than some critical material-specific limit. So what does that mean? You know, basically, if I have some Play-Doh, I apply a little bit of shear stress to it, it doesn't fail. But if I apply a lot of shear stress to it, you know, eventually it permanently deforms and eventually breaks. So when I'm and it's not just Play-Doh, it's lots of materials too. So we care about shear stress because we care about making such a comparison to some critical value. Now, let's take a moment now and think about the following situation. So pause and ponder. If I have this chunk of Play-Doh and I'm just doing a tension and just applying tension, is there any shear stress? So is there any shear stress when just stretching is there any shear stress when all I'm doing is stretching it? I'm just taking this material, I'm just taking, you know, my little chunk of material, and the only thing I'm doing is applying strictly a normal force. So take a moment now, pause and ponder what you think might be true there. Well, I suspect many of you would say no, right? You're saying, hey, wait a second, Landon. That's a normal stress, and you just told me about shear stresses. And you would be right to some extent, but with a different perspective, there actually is shear stress. So it depends on perspective. And what do I mean by depends on your perspective? Well, imagine I took an imaginary cut, but at an angle. Imaginary, so I sort of took this chunk of Play-Doh, and instead of applying a cut perfectly perpendicular like this, I took a cut and cut it at a 45-degree angle. Right, so imagine I took this Play-Doh and snipped it, sort of did like an imaginary, like an angled cut, like this, right? So I'm applying my tension like this, but I made an angled cut. Made an angled cut through the Play-Doh, right? Well, if I took this Play-Doh and pulled it apart like this, on a perfectly perpendicular surface, there's no shear stress, it's purely normal stress. But if I imagined slicing the surface like this, it turns out that there actually is shear stress in a situation that looks like that. So just imagine right? Imagine I'm looking at this face right here and I sliced it. I'm applying this force like this, but on this surface, cut like here, I could almost imagine this force as being broken down into an equivalent part that is parallel to the surface and an equivalent part that is perpendicular to the surface. So I could break it down into F perpendicular and F parallel, that the horizontal components cancel. So when I think about these two, this horizontal components cancel, and the vertical add up to the original F applied. So if I imagined not a slice perpendicular here, but rather a diagonal slice through my material, this means that this part here, there actually is some shear stress, not on an imaginary slice, horizontally through the material, but a diagonal slice. That basically means there actually is tau. And it turns out that actually when you do these material tests, when you take, if you had some new material that you wanted to characterize, and you do a tension test in it, many materials, not Play-Doh, but many materials actually don't break like with a clean horizontal cut, but actually fracture like this. And it turns out that actually if you look at x-rays of people who have broken their femur, sorry, this is a little gruesome, but if you look at x-rays of people who have broken bones, you'll hardly ever see a clean break across like this. You'll almost always see fractures. You almost always see fractures that look like this, because it turns out that bone doesn't really break when the normal stress is too high. It breaks when the shear stress across a sort of cut plane like that is too high. And it turns out you can actually predict what this sort of equivalent shear stress over a diagonal thing is, as a function of what that normal stress is. So take a moment now, pause and ponder. Imagine I took a whole bunch of different slicing angles, right? Imagine I took some slicing angle theta, right? You can imagine theta could be 0, theta could be 45, theta could be 90. Take a moment now, pause and ponder what you think the sort of equivalent, the equivalent shear stress that arises, as a function of your sort of imagined slicing angle. So take a moment now, sketch what you think this might look like. Well, it might be a little hard to predict, but if theta equals 0, we get this, we get the original normal stress, right? There should be no shear stress if we're sort of imagining this perfectly horizontal thing. So it's 0. If theta approaches 90 degrees, we actually get 0 shear stress as well. And what's the rationale there? Well, if you imagined taking a slice, that we can't slice it all the way to 90, but you can imagine slicing it very close to 90. This actually increases the cross-sectional area so much that it drives down the equivalent stress. So it's actually 0 right here. And if you're to say, hey, it's 0 at pi equals 0 and 0 at 90 degrees, or sorry, 0 at theta equals 0 and 0 at theta equals 90 degrees, but we know that at some intermediate angle, we actually have this phenomenon occurring. You might guess that this curve looks something like that, and it basically has its max at theta equals 45 degrees. And that's basically why we observe 45-degree fracture lines for bone breaks, and when we physically test materials in a materials testing machine and stretch them out, oftentimes what you'll see, not for Play-Doh, because Play-Doh is a little bit weird, but for a lot of other materials, you'll oftentimes see it sort of neck down into this sort of cone, this kind of 45-degree cone that eventually, the cone meets at the middle and the material breaks apart, something like that. So that's basically, it's not magic. Shear stress can actually appear even when we didn't really apply forces in this strictly shear stress seeming phenomenon. Now, finally, one last topic to talk about is, oh my goodness. One last topic, now that we've talked about shear stress, is to talk about shear strain. This, fortunately, is pretty simple. Shear strain is basically the deformation in response to shear stress. And what does it look like? Well, you can imagine if I were to have, some chunk of material like this, and I were to apply, that shear stress that kind of moves the top one way and the bottom the other. If I started out with a rectangle, and then I applied my shear stress, I would end up with, if the rectangle was my original shape, I would end up with something that looked kind of like a parallelogram. And the sort of magnitude by which, the magnitude by which I would sort of quantify this, this amount of deformation is basically by characterizing this angle. So this angle, this angle here is basically how we characterize this angle is how we characterize shear strain. All right, so thus concludes our discussion of stress and strain. Why we care about things not breaking and things not stretching too much. So being able to quantify stress and strain is how engineers make sure all these things work. We talked about normal stress, which is associated with a force perpendicular to a surface divided by a cross-sectional area. We talked about engineering strain, which is basically if I were to take the change in length and divide it by the original length. Then we talked about true strain, which is sort of has a weirder formula. There's a natural log in there, but that basically says, hey, that last little bit of strain that you did doesn't really count as much as that first little bit of strain that you did. So let's characterize things that way. True stress says, hey, wait a second, you don't want to divide by the original area, you want to divide by its current area if you want to predict what's truly going on. So the true stress has a correction factor that allows you to predict how much stress a material might have when its cross-sectional area has decreased due to stretching or increased due to compression. Then we talked about shear stress and shear strain, where hey, we don't always apply forces perpendicular to surfaces. Sometimes we sort of smear things out in a diagonal fashion, or even when we apply things in a perpendicular surface, if you imagine slicing something diagonally, there still can be shear stress. And shear strain is the deformation that is associated with shear stress. So, thank you very much for watching, and good luck with your study of biomaterials. Take care.